All right, so this is continuing chapter 16 notes. Still going over some I was going to say basic, some definitions and things that kind of start us on our way into in-depth discussion of acid-base. So I like to introduce the acid dissociation constant, Ka. I introduced it before when we did Ks back in equilibrium. So we have some what we call weak acids, like HA. This is a generic way of describing a weak acid. So HA is going to be the symbol that you see. Again, you're going to see a equilibrium arrow, either a double-headed arrow or a fancy one like this. Please note that you will see both in cases of having with water or without water. The only difference is you either have H plus or hydronium ion on the product side for this discussion. But because this is an equilibrium, I could write a K, which is, of course, products over reactants. So H plus and A minus is going to be over HA. So it's always going to be the same. It's always going to be the ions over the acid for this expression. And if you do have this equation to write one, please note that H3O plus is going to be what you put in for the product side here. Just know in the world of chemistry, H plus and hydronium ion are kind of interchangeable. Hydronium ion is more correct way of doing that, and I will mention that a couple different places. So this idea of equilibriums is going to be where we continue with our discussion of acid-base and some definitions that you need to know. So if you didn't recognize with our Bronson-Laurie discussions, water has an ability to be what we call amphoteric. And that is because it could take on an H or release an H. So it can act like an acid or a base. So water is always our starting point with our discussion of acid-base chemistry. So that is why we always first discuss what we call the KW, okay? And the KW is what we call the ion product constant for water, or the dissociation constant for water. And it comes from the fact that when water, okay, so if you look at this equation, two water molecules occasionally get together to make hydronium ion and hydroxide ion. Again, this is an equilibrium kind of system. So we could write a K for this, and we call it a KW because we're specifically talking about water. Water is going to be in the liquid form over on the reactant side, so that is why you typically only see H plus or hydroxide in this expression. Again, you could substitute hydronium ion for the H plus, that is perfectly acceptable. But if you take the multiplication of these two concentrations, you get a magic number, 1 times 10 to the negative 14th at 25 degrees Celsius. Well, where does 14 fall into acid-base chemistry? Have you heard of the number 14 in relationship? Well, yes, your pH scale is based off of that 14. So we're going to come back to that. Now, keep in mind that in books, you sometimes see it written as water breaking up into H plus and OH minus. I don't like writing it this way that much because the fact is water doesn't spontaneously by itself. It's one little molecule break up into H plus and OH minus. You need the interaction of two water molecules or more for this to happen. But again, if you see it in books, if you write it that way, that's going to be fine. But just know that I like to explain the real situation to you. So in continuing with our discussion of Ks here, this is a KW, we're going to talk about a Ka and a Kb in this section too. If my KW for water is 9.6 times 10 to the negative 14th at 60 degrees Celsius, and then if it goes up to 5.5 times 10 to the negative 13th at 100 degrees Celsius, is the dissociation of water endo or exothermic? So the K is increasing as I increase temperature, okay? So that means I am producing what? I'm producing more product, okay? Because my K is getting bigger. The K is, of course, the product of these two ions. So if I have more of these ions, that means I'm producing more product. So if I'm increasing the temperature, I'm shifting it to the right. So if I'm shifting it to the right, where is the heat going to be located? Well, the heat's going to be located on the reactant side in order to push this equilibrium to the right to make more of these ions. So that is why it is an endothermic process. And I don't expect you to memorize these numbers. This is more to have a discussion about Ks. All right, so these are tiny, tiny little numbers, okay? So we don't like to work with tiny numbers, so we're going to be using logs, okay? Log base 10. So that is why anytime you see a lowercase p in chemistry, it means negative log, okay? No matter what I do with these next couple calculations, okay? So if I take the pKw, I'm taking the negative log of kW. Well, what that does is essentially get rid of that 10 to the negative, and you get the 14, which is, again, what we talked about with the pH scale. So what would the pKw be at 100 degrees Celsius? You got to go back to, I got 5.5 times 10 to the negative 13. So I'm going to take the negative log of 5.5 times 10 to the negative 13. And again, plug this in your calculator. Take the negative log of that number, and you're going to get 12.26. And I will talk about sig figs for pH calculations in a little bit to kind of understand why I have 2 digits after the decimal. That's really where my sig figs come from. Do note that the larger the K is, the smaller the pK is going to be. So that is why the number went below 14 rather than going above 15. And that's going to be kind of critical. So that means at 100 degrees Celsius, your pH range is much smaller. It's from 0 to 12 and even smaller than that. So that's going to be, again, not a focus for this class, but it's more of understanding that concept of K. So where do we draw the line, or what do we focus on with acid-base chemistry in terms of what's our definition of neutral, what's our definition of acidic and basic? So neutral is not going to be where pH is equal to 7. Okay, that's not going to be an acceptable definition because it does depend on temperature. Okay, now we are going to be mostly in 25 degrees Celsius. So your Kw is always going to be 1 times 10 to the negative 14. But that is why you can't use it as a definition. Your definition must be you have equal amounts of H plus and OH minus. That has to be your definition. Now, you can say hydronium ion instead of H plus. That's acceptable. But if I have a neutral solution, if I take the negative log of my hydrogen ion concentration, I have my definition of pH, okay? So pH is the negative log of H plus, negative log of H plus. So my pH is at 7 at a neutral solution at 25 degrees Celsius. What would my pH be at 100? Well, I know that a pH of 7 means I have 10 to the negative 7th of both my H plus and my OH minus, okay? Because what it's doing is getting rid of that 10 negative. So if my range goes from 0 to 12.6 for my 100 degrees Celsius, my middle range has to be 6.13, okay? Now, what's going to be key to our discussion is, besides pH, is something called POH, okay? Now, POH is the same as pH, except you're taking the negative log of the hydroxide concentration. Now, everything in chemistry is based off the pH scale, but you can look at POH as well. The fun thing about pH and POH at 25 degrees Celsius is they always add up to 14. So that's going to be helpful in some calculations we're going to be doing. And please note that when you multiply the concentration of your two ions, you will always get 10 to the negative 14. So again, that's another way you can do these calculations. So to kind of round it out, acidic solutions are where you have more H plus than you do OH. And so your pH is going to be somewhere below 7. Now again, I'm not going to be like, what is the pH? You know, is it 6.9? Is that acidic or not? But you could say anything below 7 is considered to be acidic. While basic, your OH minus is the bigger value, so you could write it in any which way you want. And your pH is going to be greater than 7, going to be greater than 7. So again, that's going to be, you know, anywhere from 7.1 to 14. And again, there's not going to be hard, fast rules for how to judge that. Okay.